So, let us continue concentration polarization, and what we have seen earlier, that if this is distance from the metal surface and this is we are considering cathodic reaction. Now, that case, if you see the concentration profile from the metal surface to the bulk of the solution of concentration profile of N plus ion. So, that means this is my C, which is the bulk concentration, and initially we have started with C0 and then with the progress of reaction, and if the rate of actual charge transfer reaction, that is the anodic, that is the activation process rate, is higher than the rate at which metal ion is supplied from the bulk to the interface. If that activation polarization activation, the rate at which metal transfer occurs, charge transfer occurs, rate at which this actual reaction happens, that is higher than the rate at which metal ion is supplied from the bulk to the interface, then we experience concentration polarization, or rather concentration change from the interface to the bulk of solution, and this is C, and we have seen that this is boundary layer, and we have seen that if we follow simplistic approach, that is the Fick's first law of diffusion, then I is related to minus NF D, which is diffusivity of that metallic ion in the medium, C0 minus C by delta, considering a linear concentration change. Then we have also seen that this concentration at this interface will go to 0 if the current is maximum. That means, when the current is maximum, that means whatever charge is coming from the bulk to the interface, those are getting reduced. So, in that case, I max would be equal to minus NFD. Here C, since C is 0 at this interface, then C would be 0. So, C 0 by delta. Now, then we have followed Nernst equation just to understand what is the potential at these two interfaces. So, at this two position bulk, if the concentration at this interface, if the concentration is C0 and if the concentration is C, then what would be the potential, and that would be decided by concentration potential, concentration effect. If we have already seen that if the concentration of metallic species increases, then the electrode potential also will increase. So, if we write the Nernst equation, works in this case M n plus M would be equal to E 0 n plus M plus R T N F into 2.303. I am putting in the form of log C. Now, one case it is C, that means when the concentration goes to C at the interface, and one case it is C0, that means when time equal to T equal to 0, when with the just start of the process of concentration difference, then there would be two potential. One is, let us say this is 2, and one case it would be E1, the initial condition, that is M n plus M. So, this term will remain because this is a constant term. Now, these other terms will also remain, and here you have to put C0. C0. Now, since C0 is greater than C1, so E2 Mn plus M should be less than E1 M plus M. Now, you see, initially we have started with C0, now we have reached to C. That means we are having concentration lowering in concentration, and that would lead to lowering potential. And also this is a cathodic reaction. We have already seen that for a cathodic reaction, if it proceeds, then we get cathodic polarization. And the cathodic polarization here also, since the cathodic polarization concept is maintained, because the potential is dropped with the progress of this reaction, cathodic reaction, and at the same time this effect is coming because of change in concentration. So, this is a cathodic concentration polarization that would lead to lowering in potential. Now, we have to quantify this polarization, cathodic concentration polarization. Then we can write that this concentration, which is in the cathodic case, that would be E2 minus E1 would be equal to, now let us say this process is taking place at 25 degrees Celsius temperature and 1 atmosphere pressure. Now, we know what is R. I am just putting the value F, this is joule per mole per Kelvin, this is F is nothing but 96500 roughly coulomb per gram equivalent. Now, if you put all those values, you would see that these two terms will get cancelled, because we are seeing what is the potential difference because of concentration change. There is the final potential, which is this, minus the initial potential, then it will lead to 0.059 by n log of C by C0. Now, C by C0 we can write it as, we can write 1 minus 1 plus C by C0, this would come C0 minus C by C0. Now, we know that C0 from this equation, C0 by minus C would be equal to I delta NFD. Similarly, C0 from this we can get C0 equal to I delta NFD. Let us put this values instead of C0 minus C and C0, then we would get 1 minus I by I max, which is the ratio between current densities. So, let us put this, I will just replace this C by C0, instead of C by C0 I will just write this. So, it would 1 minus I by I max. So, this is an important equation, and this quantifies the concentration polarization. And since this is in the log scale, so you will see that if you, for example, we have seen the activation polarization, we have seen that if this is a 0 value, it varies like this. We have seen that. And what are those two components? this is anodic component and this is cathodic component. Now, in this case, when I equal to 0, then definitely this should be almost parallel. Then once I increases, this I increases and goes close to I max, then this term would become infinite. So, my concentration polarization case will be following this track, this nature. This is my concentration polarization. So, now here at this position I equal to I max, and hence this becomes infinite. So, this is my concentration polarization expression or quantification, and this is my plot. But if you can see that when I is less than I max, then what is the effective polarization? I equal to I max, then it is infinite, but when I less than I max, let us say before it reaches close to I max, then polarization, concentration polarization is almost 0. But that times what polarization is active? Since there is no change in concentration, that means at a lower current value there is no change in concentration at the interface. So, you do not experience any concentration polarization, but still there would be active polarization, and that active polarization will take the potential to the lower side or to the negative side for a cathodic reaction. So, cathodic polarization is active, this line cathodic polarization is active. Now, when it reaches to this level, so cathodic polarization will no longer be the controlling issue factor. So, that time we have come across to this level, which is a very high current, which is this current, and that time I equal to I max, this point. So, then we will, if we extend this scale, this potential scale, then it would be like this. So, my actual experimental polarization curve will be only, I am just putting only this part, only this part. Only this part. So, rest of the part will not be there. This is my situation. Now, so I will get this is my polarization if we only consider the cathodic polarization. Now, let us have some important information or important aspects of concentration polarization. Now, if you see the expression for I max, now let me write I max separately. Delta. Now, let us say if I increase the temperature, what would happen? If I increase the temperature, then my diffusivity would increase. The rate at which ionic species are moving in the solution, that would increase, the speed would increase. So, if diffusivity increases, then what would happen to Imax? Imax would increase, since N, F and C0, the bulk concentration is not changing, and so this would Imax would increase. Now, let us say I consider one O2 molecule, the diffusivity of O2 molecule or DO2 in water and DH plus, the diffusivity of OO2 would be less than DH plus, since this is a very small atom, a small size ion, whereas this is a molecule which is of a big size. So, it is of course, it is very easy to diffuse H plus ion compared to O2. So, sorry, this diffusivity of H plus ion would be larger than would be more compared to diffusivity of oxygen, and now that case I will see that Imax correspondingly Imax H plus would be greater than Imax O2. This is a size effect. Now, temperature effect, for example, in particular case, let us say H plus ion, let us say one is at T1, one is at T2, then diffusivity of H plus at T1, and if you say that T1 is greater than T1 is greater than T2. So, then at T1, which is at higher temperature, diffusivity of H plus ion would be greater than D H plus T2, and correspondingly from this equation, if diffusivity increases, there would be increase in Imax, which is the maximum current, where whatever ions that are coming from the bulk solution to the interface, those will get reduced. So, hence the concentration at this interface would go to 0, that means C would start from 0. So, that case I will see that I max H2 H plus at T1 greater than I max of H plus ion at T2. So, what are the effects of this situations, size effect as well as size effect of this diffusing species as well as temperature? We will see the difference here. Now, Imax, if Imax increases, so I will experience the Imax, let us say Imax increases in this case. Imax increases means I will experience this Imax point here. So, in order to reach to that Imax, I will have to still have some sort of concentration anodic activation polarization, then it will meet and then it will proceed further. So, this part again goes off. So, this curve is when this is let us say this is I max 2, this is I max 1, and the relation between I max 2 and I max 1 is this. So, I will see that this activation polarization still continues until it reaches, the current reaches to I max, then the polarization would be governed by concentration effect, and that time it would be infinite polarization. Now, this effect can be due to this or due to this. Let us have one example, what happens if we have this situation, because we experience O2 reduction or dissolved oxygen reduction and hydrogen ion reduction in water medium. Let us plot it here. So, this is log I. Now, let me remove this part. Let us say if it is acidic medium. So, if pH of the medium is less than 7, then and if the water contains dissolved oxygen, then there could be two reactions, two cathodic reactions. And there could be one more reaction. This is one reaction and this is one reaction. Now, let me plot the polarization effect starting from I equal to 0. So, that case, this is my polarization axis, which is this. Let me put this is as 0. Now, when and this potential is about 0. It is about 1.23 volt. So, the potential at which this will start, which is 1.23 volt, and this in case this is E0 value, and here E0 value is 0 volt. So, if you consider the absolute potential for this case would be where this reaction has reached equilibrium, because we have to start from the equilibrium value, since the polarization says that the deviation of potential from the equilibrium value. So, then this value, this point will be lying above this point corresponding to this reaction. So, let us say this is E. In that case, this would be 1.23 volt and 0 volt would be, let us say, at this point, let us say this point 0 volt. Now, if you consider polarization, now let us, this axis is potential and this axis is, let me plot it. This is potential axis, absolute potential on the basis of absolute potential. Let us say this one is with respect to polarization. Now, this reaction, if you consider the polarization, will start here, and that case the value of this point would be 1.23 volt, if we consider that this is all the species are maintained at unit activities or the standard reduction potential if you consider. Now, then initially activation polarization will occur. Initially activation polarization will occur. So, now let me plot only the cathodic line. So, activation polarization for cathodic line would be beta C log of I C by I 0. Now, this is my I 0, this is my I 0 point or log I 0. My line would be this. So, this is I0. Now, what would be my I max for O2? That would be decided by D value as well as C value in the water, and delta, which is decided by diffusivity of the water molecule at this O2 molecule in water. So, let us say that value is corresponding to this, which is I max O2. Now, as polarization is taking place, current value is increasing, and once it reaches to I max of O2, it will start following this path. And before that, if you consider only the cathodic polarization, this is 0. So, this is like this. This is like this, but actual situation would be following this line, polarization line would follow this. Now, let us say this is my 0 volt, and once we reach to 0 volt, that means we are coming across hydrogen evolution reaction. So, hydrogen evolution reaction, then it will start hydrogen evolution reaction. Once it reaches to this, as you go further down, if you go further down the polarization, if we are further having polarization or cathodic polarization, then it will come across this reaction and it will start following the activation polarization for this. So, if you independently plot the activation polarization of this reaction, so it would be this. So, then you see, once we reach to this, it cannot follow this line, because by the time you experience another polarization, because of that current value is further increasing. Here the current value remains constant. So, the line will take a bend and it will follow like this. Now, as we have seen that I max O2 is less than I max H plus. So, by the time it reaches H plus, it will keep continuing along this activation polarization line for hydrogen cathodic reaction. So, then you will see that there would be one more bend, which is nothing but I max H plus ion, which is the maximum current density for the hydrogen ion evolution, hydrogen gas evolution or this cathodic reaction. So, this would be my sequence, and if you would like to see the individual situation for hydrogen concentration polarization, this is my hydrogen concentration polarization, this is my oxygen concentration polarization, this is my oxygen, this is my oxygen concentration oxygen cathodic polarization or activation polarization, this is my activation polarization for hydrogen evolution, hydrogen this reaction, and this is my I max for hydrogen evolution reaction, H2 gas evolution reaction or this cathodic reaction. So, this would be my complete plot. So, it will start from here, it will go like this, then it will go like this and like this. So, this is my overall situation as you come across different species, different activation polarization and concentration polarization. And now you see for oxygen evolution, oxygen this reaction, so this is my 0 over voltage, and for hydrogen evolution or this cathodic reaction, this is my 0 over voltage. but total polarization would be this much. If you consider, let us say I am at this current value, if I have increased current value to I max of H plus, let us say I am here. So, my total polarization would be this much, and if you would like to see the what would be the polarization for hydrogen cathodic reaction, this cathodic reaction, this is individual hydrogen polarization due to hydrogen, rather I would write polarization due to hydrogen, and this is my total polarization. Now, if you would like to measure the total polarization, now you see the total polarization is nothing but the addition of concentration polarization as well as activation polarization. Now, let us say I am here, I am at this point, at this position, what would be my total polarization? Total polarization would be this much, and this is total would be equal to polarization due to activation from here to this. So, polarization due to activation is this much, and polarization due to, that means this is nothing but NC, which is cathodic over voltage due to activation polarization, and this is my concentration. For concentration polarization, I would write neta CONC, that means concentration, and this is for cathodic. So, this is, and here I can put activation. So, this is would be equal to concentration. So, this is my total polarization. Now, point is we are considering only the cathodic concentration polarization effect, but there could be the also some amount of anodic polarization which is also due to concentration effect, but generally we do not come across anodic concentration polarization. The reason for this is there are two possible reasons. There are two possible reasons why we do not experience anodic polarization. One is accumulation. Whenever we see that for anodic side you are always producing metal ion, that means this reverse reaction is taking place. Now, there will be accumulation of metal ion just at the interface. So, concentration would be, let us say initially you started with C0 for the metal ion, then concentration would increase at this interface. Just reverse would happen. What is happening in case of cathodic case? Concentration is decreasing from the initial concentration, and here concentration should increase from the initial concentration. So, whenever you have accumulation of this metal ion at this interface, most of the cases we form some sort of corrosion product. First reasons why anodic concentration polarization not considered. So, first case is corrosion product. Corrosion product formation at the interface, and once we have corrosion product formation, there would be passivation. That passivation part it would be considered in detail later. Now, second reason is this limiting current or Imax. This is also called IL. Also called IL. IL means I limiting. So that means this is the maximum current density that is possible where potential polarization would become infinite. So this IL is significant during reduction process, and in case of anodic case you see that even if the product is not forming, there is a huge amount of metal ion supply. So you do not experience any sort of metal ion depletion at this interface. So there is almost unlimited supply of metal ion because of this process. So this because of two reasons we do not generally consider anodic concentration polarization effect. So we see there are two polarization effect, one is activation polarization, another one is concentration polarization, and we also see that concentration polarization is most effective in case of cathodic reaction, and we have also quantified the amount of polarization from the current value or the current which is going through the circuit, short circuited path. Now we have seen that there are two polarization, one is activation effect would be beta, which is Staffel slope. It can be for anodic A, for cathodic it is C, log of I, which is in case of anodic it is A, which is C for cathodic, divided by the exchange current density for that cathodic reaction. And similar way we have also seen concentration is nothing but 0.059 by n, and this n is coming because we are considering this reaction. So log of 1 minus I by I max, and instead of max we can also write IL. So this is the concentration polarization. Now there is one more polarization which is called resistance polarization. Resistance. Now whenever current is flowing into the electrolyte, there would always be some amount of resistance to the charge transfer because of inherent resistance of the water, or inherent resistance of the electrolyte. Now if R is the resistance of the electrolyte, then I is the density, or in this form case if this I is my current, absolute current in the system, then IR is my resistance drop. This is IR is my resistance polarization. IR is nothing but the volt. So this much potential will drop. Now the implication of this resistance polarization we will see in when we come across mixed potential theory. And then what is my total over potential? It would be combination of all these three. So once we know this, now we can understand how the rate reactions, all the corrosion reactions or the electrochemical reactions are taking place in a particular system. Now for that we need to understand, along with this polarization, this is polarization, we need to also understand the mixed potential theory. So let us talk about mixed potential theory. Now this on the basis of this theory, we can understand many of those practical corrosion problems or corrosion examples. Now, I will start mix potential theory. This theory was introduced by Wagner and Trend in 1938, and this is a very important aspect of understanding corrosion effect. And it is based on, this theory is based on two postulates or hypothesis. One hypothesis, it says, I am just writing the whole thing, any electrochemical reaction can be divided into two or more partial oxidation and reduction reaction. Now, for example, zinc corrosion in acidic medium, which is deaerated, there is no oxygen. So, zinc plus H2O, it would form zinc OH whole 2. Zinc corrosion in H2 medium, zinc will form zinc plus plus ion, and on that, because of this process, it will release 2 electron, and hydrogen will accept that this 2 electron and form H2. So, my reaction would be zinc plus H plus is going to zinc plus H2. So, this is 2H plus. So, this is my actual reaction, what is happening in acidic media, which is deaerated HCl, let us say. Deaerated HCl, if you put one zinc rod, the actual reaction is like this. Now, this reaction we can divide it into, you can divide into two parts. One is oxidation and another one is reduction. So, now the one electrochemical reaction is divided into one oxidation and one reduction process. Now, if it is not deaerated, then there would be one more cathodic species, cathodic reaction that can be possible in this medium, which is O2 plus 4H plus 4E going to 2H2O. So, this reaction can also happen, and which will enhance this zinc to zinc plus plus. So, that case one more reaction, you just have one more reaction, this cathodic reaction plus one more cathodic reaction. These two reaction would happen and one anodic reaction or oxidation reaction. So, If it is aerated, if it is deaerated, then there will be one oxidation, one reaction, and if it is aerated, then there would be one oxidation reaction and two cathodic reaction, this one as well as this one. So, you see the statement, any electrochemical reaction. So, finally the zinc reduction process, which can be divided into two or more partial oxidation and reduction reaction, and here one oxidation and two reduction reaction in if it is aerated, and if it is not aerated, only H plus ion. So, then there would be two partial reactions. So, the statement says that. The second statement says that there can be no net accumulation of electric charge during an electrochemical reaction. During electrochemical reactions. Now, you see what it says, this says charge conservation. This is nothing but charge conservation. This is nothing but charge conservation. Now, we get back to this. Let us say if it is deaerated, now you consider this set of reaction. If it is deaerated, zinc is going to zinc plus plus, 2 electrons are released. Now, these two electrons will not remain as free electrons. These 2 electrons will be consumed by hydrogen ion, and then hydrogen gas will generate because of this reduction reaction. So, now you see this, whatever charge is generated because of anodic process or oxidation process, that charge will be consumed by some cathodic process or reduction process. That means, the total charge should be 0 after whole reaction. So, that says the charge conservation. Now, let us say if it is aerated, then you have 2 electrons for this reaction, which is generated due to zinc to zinc plus plus ion formation. That 2 electrons are consumed by 2 H plus ion. Now, you have the possibility of having one more cathodic reaction. So, where from it would get 4 electron? So, 4 electrons have to be supplied from these reactions. So, the equal amount of electron should be generated from this reaction in order to have these 2 cathodic reactions. So, the overall electron generation per unit time would be equal to overall electron consumption per unit time. So, it says that overall electron consumption rate would be equal to overall electron generation rate. So, once these two are equal, that means the overall electron consumption because of cathodic reactions should be equal to overall electron generation due to anodic reaction. And now again, what is this? This is what? This is what? This is nothing but the cathodic current. So, that means this is nothing but IC, cathodic current, and this is nothing but IA, and we see that these two are equal, but these two things are happening in opposite directions. In order to understand that the directional nature of these two currents, we put a negative sign in front of a cathodic current density. So, we see that cathodic current density is equal to anodic current density. Now, what is corrosion? Corrosion is nothing but the overall electron generation rate, or IA, or the dissolution rate. So, this is equal to I core or corrosion current.